Tonight, we are going to travel to the edge of everything we thought we understood about the cosmos. We are going to confront a discovery so enormous, so fundamentally destabilizing to our models of how the universe works, that the scientists who found it spent years checking and rechecking their data before they were willing to say what they had actually found. And when they finally said it, the cosmology community did not celebrate. It did not erupt in excitement. It went quiet in the way that rooms go quiet when someone says something that cannot be unsaid. What they found is a structure, a thing, a coherent, connected, measurable object embedded in the fabric of the observable universe, and this object is so large that if you were to travel from one end to the other at the speed of light, the journey would take you 10 billion years. 10 billion years at the fastest speed anything in this universe is permitted to travel, and you still would not reach the other side. Our entire solar system has only existed for 4.5 billion years. The universe itself has only existed for 13.8 billion years. And yet here is this thing, this structure, spanning a distance that swallows 10 billion years of light travel time as if it were nothing. Its name is the Hercules Corona Borealis Great Wall. It is the largest known structure in the observable universe. And according to everything we thought we knew about how the cosmos is arranged, how matter distributes itself across the largest scales, how the universe evolved from its earliest moments to the vast architecture we observe today, this structure should not exist. It cannot exist. The mathematics of cosmology, the most successful and rigorously tested framework for understanding the large-scale universe, explicitly forbids the formation of anything this large. And yet, there it is. By the time this exploration is finished, you will understand not just what this structure is and how it was discovered, but why its existence forces us to confront uncomfortable questions about the foundations of modern cosmology. You will understand the principle that sits at the heart of our entire model of the universe, a principle so fundamental that we have built our entire understanding of cosmic history on top of it, and you will understand why this structure, by simply existing, challenges that principle at its deepest level. You will understand what it means for something to exist that the universe should not have had enough time to build, and you will sit with the unsettling possibility that our map of reality, as detailed and precise and mathematically beautiful as it is, may be missing something enormous. If what we are about to explore stirs something in you, if it makes you want to think more carefully about the universe and your place within it, consider sharing this with someone who might feel the same pull. The questions at the heart of this story are the oldest and most important questions our species has ever asked. They deserve the widest possible audience. Now, let us begin with the universe itself, because to understand why this structure is so troubling, you first need to understand the picture of the cosmos that we built before anyone found it. For most of human history, the universe was not a subject of scientific inquiry in the modern sense. It was a subject of mythology, theology, and philosophy. The night sky was a ceiling, not a depth. The stars were fixed points of light embedded in a sphere rotating around the earth, and beyond that sphere there was nothing. Or there was the divine, or there was something so beyond human comprehension that the question was not even worth asking. This was the universe as our ancestors understood it, and for thousands of years no one had the tools to do better. The revolution came slowly, then all at once. In the early decades of the 20th century, our understanding of the cosmos underwent the most dramatic expansion in the history of human knowledge. It began, as so many revolutions begin, with a disagreement about a point of light. In the early 1920s, astronomers were engaged in what was called the Great Debate, a genuine scientific controversy about the nature of certain fuzzy patches of light visible through telescopes. These patches were called nebulae, from the Latin word for cloud, and there were two competing interpretations of what they were. One interpretation held that these nebulae were clouds of gas and dust within our own Milky Way galaxy, interesting objects certainly, but local, nearby, part of the same system that contained our Sun and every star we had ever named. The other interpretation held that these nebulae were not clouds at all. They were entire galaxies, systems of hundreds of billions of stars like our own Milky Way, and they were so impossibly far away that they appeared as mere smudges even through the largest telescopes of the era. The debate was settled in 1924 by an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California. Hubble was using what was at the time the most powerful telescope in the world, a 100-inch reflector perched on a mountain above the Los Angeles basin. He was studying a nebula called the Andromeda Nebula, and within it he identified a particular type of star called a Cepheid variable. These stars are extraordinary because they pulse. They brighten and dim in a regular rhythm, and crucially, the period of that rhythm, the time it takes to complete one full cycle of brightening and dimming, is directly related to the star's intrinsic luminosity. How bright it actually is regardless of distance. By measuring how bright a Cepheid appears from Earth and comparing that to how bright it truly is, you can calculate exactly how far away it must be for its light to have dimmed to what you observe. Hubble measured the Cepheids in Andromeda and found a distance that ended the debate permanently. The Andromeda Nebula was not a local cloud of gas. It was a galaxy, a system of stars roughly similar in scale to our own Milky Way, and it was approximately 900,000 light-years away from us, a number that we now know was actually an underestimate due to a calibration error that would not be corrected for decades, but even the underestimate was staggering. Andromeda was not part of our galaxy. It was entirely separate, and enormously far beyond our galaxy's edge. The nebulae were not clouds. They were island universes, and space did not end at the boundary of the Milky Way. Space continued outward, filled with galaxies for distances that dissolved the mind. This single discovery expanded the known universe by a factor that is almost impossible to express. Before Hubble, the observable universe was essentially the Milky Way, a disk of stars perhaps 100,000 light-years in diameter. After Hubble, the universe was a vast three-dimensional ocean filled with galaxies as far as any telescope could see. The question was no longer how large the Milky Way was. The question was how large the universe was, how many galaxies it contained, and how they were arranged. The answer to that last question, how galaxies are arranged across the cosmos, would take another half-century to begin to emerge. And when it did, what astronomers found was not chaos. It was not a random scatter of galaxies distributed uniformly like raisins in bread. What they found was structure, hierarchy, pattern, and the story of how they discovered that pattern and what it told them about the universe is essential background for understanding why the Hercules Corona Borealis Great Wall is so disturbing. In the 1950s and 1960s, astronomers began the painstaking work of mapping the universe in 3 dimensions. This required not just identifying galaxies in the sky, which a photograph could give you, but determining how far away each galaxy was, which required spectroscopy. When you spread the light of a galaxy through a prism-like instrument and examine its spectrum, you find dark absorption lines, specific wavelengths of light that have been absorbed by atoms in the galaxy's atmosphere. These lines correspond to known elements, hydrogen and helium and calcium and iron and dozens of others, and they appear at known wavelengths in laboratory conditions on Earth. But when you look at a distant galaxy, these lines are not at the expected wavelengths. They are shifted. Specifically, they are shifted toward the red end of the spectrum, toward longer wavelengths, toward lower frequencies. This is the famous redshift, and it is caused by the expansion of the universe itself. Space is expanding, and as it expands, it stretches the wavelengths of light traveling through it. The more space between us and a galaxy, the more that light is stretched, and therefore the greater the redshift. Measure the redshift. Apply the mathematics of cosmic expansion, and you can calculate the distance. This process, measuring the redshift of thousands and then tens of thousands of galaxies, is extraordinarily time-consuming. Each galaxy requires hours of telescope time to collect enough light for a reliable spectrum. For decades, progress was slow. Astronomers had catalogues of galaxy positions on the sky, their locations in 2 dimensions like coordinates on a map. But the 3rd dimension, depth, remained elusive. Without depth, you could not know whether 2 galaxies that appeared close together in the sky were actually neighbours in 3-dimensional space, or whether they happened to be aligned along the same line of sight, but separated by hundreds of millions of light-years. The first major 3-dimensional maps began to emerge in the 1980s, and what they revealed was astonishing. Galaxies were not distributed randomly through space. They were not even distributed in simple clusters, gravitationally bound groups of a few dozen or a few hundred galaxies orbiting a common center, though those clusters existed too. What the 3-dimensional maps revealed was something far more elaborate and far more beautiful. Galaxies were arranged in vast sheets and filaments, enormous flat walls of thousands of galaxies stretching across hundreds of millions of light-years, connected by thin threads of galaxies called filaments, with vast empty regions, enormous spherical voids containing almost no galaxies at all, filling the space between the walls and filaments. The universe, at the largest scales anyone had mapped, looked like a cosmic web, like foam, like the structure you would see if you looked at a bubble bath from very close up and could somehow see the bubbles stretching across you hundreds of millions of light years. The discovery of this cosmic web structure was one of the great revelations of 20th century astronomy. It had profound implications, not just for our understanding of how galaxies are arranged today, but for our understanding of how the universe began and how it evolved. Because the cosmic web is not random, it is the direct product of physics operating over billions of years, a physics that we can calculate and model and test. And the story of how the cosmic web came to exist takes us all the way back to the first moments after the Big Bang. In the earliest fraction of a second after the universe began, space was filled with an almost perfectly uniform sea of energy and matter at temperatures so extreme that no atom, no nucleus, no particle as we know them today could exist. Everything was plasma, a soup of fundamental particles interacting constantly at energies that made the cores of today's most violent stars look cool and quiet by comparison. The key word there is almost perfectly uniform. Not perfectly uniform, almost. Across this primordial sea of energy, there were tiny fluctuations, regions where the density was very slightly higher than average and regions where it was very slightly lower. These fluctuations were not large. We are talking about variations of roughly 1 part in 100,000. One region of space might have had a density that was 100,001 parts per 100,000 of the average, while the next region had a density of 99,999 parts per 100,000 of the average. The difference was almost nothing. Almost, but almost nothing, given enough time and the relentless pull of gravity, becomes everything. Gravity is patient. Gravity does not care about the time scales that matter to living things or to civilizations or to species or to planets. Gravity operates on timescales measured in billions of years, and on those timescales, even the most infinitesimal difference in density becomes enormously significant. The regions that were ever so slightly denser than average exerted slightly more gravitational attraction on surrounding matter. They pulled in more matter from their surroundings, which made them denser still, which made them pull in even more matter, which made them denser still. A feedback loop of gravitational collapse operating over hundreds of millions, then billions of years. Meanwhile, the regions that were slightly less dense than average lost matter to their denser neighbours. They became emptier, which reduced their gravitational influence, which caused them to lose even more matter to the surrounding dense regions. They became the voids. The original tiny fluctuations in the density of the early universe were the seeds of everything we see today. Every galaxy, every cluster, every filament, every wall, every void in the observable universe traces its origin to those 1 in 100,000 density variations in the first fraction of a second after the Big Bang. This is not speculation or metaphor. We can observe the original fluctuations directly. They are imprinted in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky, and the pattern of fluctuations in that radiation matches, with extraordinary precision, the pattern of large-scale structure we observe in the distribution of galaxies today. The universe grew from those seeds exactly as our physics predicted it would. The cosmic web is a natural consequence of gravity, time, and those tiny original imperfections. But here is the critical constraint, the constraint that lies at the very heart of why the Hercules Corona Borealis Great Wall should not exist. Gravity had a limited amount of time to work. The universe is 13.8 billion years old. That sounds like an enormous span of time, and by human standards it is incomprehensible. But by the standards of what gravity can accomplish at cosmological scales, 13.8 billion years imposes strict limits on how large a coherent, gravitationally influenced structure can become. Think of it this way: gravity cannot act faster than the speed of light. Gravitational influence, like all physical influence, propagates at light speed. This means that two regions of the universe that are separated by a distance greater than the universe is old, in light years, have never been able to communicate with each other through any physical mechanism. They have never been in causal contact. Whatever happens in one region has had no way to affect what happens in the other region, because the signal carrying that effect, travelling at the maximum possible speed, has not had enough time to bridge the gap. This is the concept of the cosmological horizon, and it defines an absolute upper limit on the scale of causally connected structures. 2 points that are farther apart than light could have travelled since the Big Bang cannot have been influenced by the same physical process. They cannot have been shaped into a coherent structure by gravitational collapse acting between them, because that collapse requires causal contact, and causal contact requires time, and time, while plentiful, is finite. Our best cosmological models, running on our most powerful computers, simulating the evolution of the universe from the Big Bang to today, produce cosmic webs full of structures, walls, filaments, clusters, voids. These simulations match the observed universe with remarkable fidelity across enormous ranges of scale. They correctly reproduce the size and distribution of galaxy clusters. They correctly reproduce the typical sizes of cosmic voids. They correctly reproduce the network of filaments connecting dense regions. The agreement between theory and observation is one of the great triumphs of modern cosmology. And in all of those simulations, in all of those models, the largest coherent structures that form are roughly 1.2 billion light-years across. That is the theoretical upper limit. That is the scale beyond which gravity has not had enough time to organize matter into a coherent entity. Structures larger than roughly 1.2 billion light-years should not form, cannot form. The physics is unambiguous about this. The number has been checked and rechecked and independently derived through multiple approaches, and it consistently comes out to roughly the same value. 1.2 billion light-years. That is the ceiling. The Hercules Corona Borealis Great Wall is 10 billion light-years across, not 10% larger than the theoretical maximum, not twice the theoretical maximum, not even 5 times the theoretical maximum, more than 8 times larger than anything the universe should have been able to build, 8 times beyond the hard limit that our most sophisticated models place on structure formation, a structure so large that it strains the very concept of a structure, so large that some cosmologists have questioned whether it deserves to be called a single connected object at all, while others have looked carefully at the data and concluded that yes, it is real, it is coherent, and it should not be there. To understand how something like this was found, you need to understand what astronomers were doing in the early 2000s and why a particular class of violent cosmic explosions became, almost accidentally, the most powerful tool anyone had ever used to probe the large-scale structure of the universe at the greatest distances ever mapped. Gamma-ray bursts are the most energetic explosions in the observable universe. They are so energetic that in the span of a few seconds to a few minutes, a single gamma-ray burst can release more energy than our Sun will emit over its entire 10 billion-year lifetime. They are so energetic that they are detectable across the entire observable universe, their light reaching our instruments from distances measured in billions of light-years, from times when the universe was a fraction of its current age. They are so bright that for the duration of their brief existence they outshine entire galaxies, visible across gulfs of space that would render any ordinary star invisible. Gamma-ray bursts come in 2 varieties, distinguished primarily by their duration. Short gamma-ray bursts last less than 2 seconds and are now understood to result from the collision and merger of 2 compact stellar remnants, neutron stars or black holes, spiraling together over billions of years until they finally touch, at which point the resulting cataclysm releases energy in a focused jet of gamma radiation. Long gamma-ray bursts last more than 2 seconds, sometimes for minutes, and they result from the collapse of a massive star's core at the end of its life, a particularly violent form of stellar death in which the collapsing core forms a black hole and channels the infalling material into polar jets that punch through the dying star and emerge as focused beams of some of the most energetic radiation in the universe. What matters for our story is not the mechanism. What matters is the brightness. Because gamma-ray bursts are so extraordinarily luminous, and because they occur throughout the universe wherever massive stars live and die, or wherever neutron stars eventually find each other, they serve as beacons scattered more or less uniformly across the cosmos. They are not clustered in particular regions, they occur at all redshifts, at all distances, in all directions. They are, in other words, a sample of the universe itself, probes of the cosmic distribution whose positions, when mapped in 3 dimensions, can reveal the large-scale structure of the universe at distances where galaxies themselves become too faint for conventional spectroscopic surveys to reach. This is why a group of astronomers, led by a researcher named István Horváth and his colleagues at the National University of Public Service in Budapest, Hungary, began analyzing the 3-dimensional distribution of gamma-ray bursts in the early 2000s. Their database was the largest catalogue of gamma-ray burst positions and distances assembled to that point, built from decades of observations by multiple spacecraft, including the Compton Gamma Ray Observatory and the Swift satellite. By 2014, this catalogue contained hundreds of bursts with measured redshifts, giving each burst a precise position in 3-dimensional space. What Horváth and his team set out to do was ask a simple question. When you plot all of these bursts in 3 dimensions and look for clustering, do you find structures? And if so, how large are those structures? The answer they found was not simple at all. When they plotted the positions of gamma-ray bursts, with redshifts placing them between roughly 1.6 and 2.1 billion years after the Big Bang, a particular region of the sky came alive. The bursts in that region were not distributed randomly, they were clustered. They formed a connected overdensity, a region where the density of gamma-ray bursts was significantly higher than what you would expect from a uniform distribution. The clustering was not subtle. It was pronounced enough that the team calculated the probability of observing such a pattern by random chance alone at less than 1 in 20,000. That is a statistical confidence level above 99.995%. In the language of physics, where a 5 sigma detection is the conventional threshold for a genuine discovery, this exceeded that threshold. The structure they had found sat in the direction of 2 constellations visible from the northern hemisphere. One constellation is Hercules the hero, one of the largest and most ancient of the classical constellations, a great figure of mythology kneeling in the sky with his club raised. The other is Corona Borealis, the northern crown, a small but distinctive semicircle of stars arcing just north of Hercules. The structure was named for both of them, the Hercules Corona Borealis Great Wall. And when Horváth's team calculated its size, the room went quiet. The structure spanned approximately 10 billion light-years, not in one dimension like the length of a rod, but as a coherent overdensity, a region of space with a measurably higher concentration of matter than its surroundings, extending across 10 billion light-years in its longest dimension. To put that number in context, consider that the entire observable universe, the full sphere of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall occupies roughly 1/10 of the diameter of everything we can see. It is not a small anomaly hiding at the edge of our maps. It is a dominant feature of the observable universe, a structure so vast that it covers a significant fraction of the entire cosmic canvas available to us. Compare it to other large structures and the numbers become even more difficult to absorb. The Great Wall, discovered in 1989 by Margaret Geller and John Huchra at the Harvard Smithsonian Center for Astrophysics, was at the time the largest known structure in the universe. It is approximately 500 million light-years long and 250 million light-years wide. It was considered so large that its discovery caused genuine consternation in the cosmological community because it approached the theoretical limits of what gravity could build. When the Sloan Great Wall was discovered in 2003 using data from the Sloan Digital Sky Survey, it pushed the record to approximately 1.4 billion light-years in length, right at the edge of the theoretical ceiling. Cosmologists noted the tension with existing models but found ways to accommodate it within the framework, arguing that the Sloan Great Wall was perhaps an extreme outlier, a rare statistical fluctuation, a one-in-a-million event that the universe managed to produce without violating the underlying physics. The Hercules Corona Borealis Great Wall does not permit that kind of accommodation. It is not an extreme outlier at the tail of an expected distribution. It is not a one-in-a-million event. It is 7 to 8 times larger than anything in the theoretical distribution. It is not a challenging data point that pushes the boundaries of the model. It is a data point that sits so far outside the model's predictions that the model cannot be stretched or tweaked or statistically massaged to include it. If the Hercules Corona Borealis Great Wall is real, and the statistical evidence says it is, then something fundamental is either wrong with our understanding of how large-scale structure forms, or wrong with the assumptions that underlie our entire cosmological framework, or both. But before we can grapple with what this structure means, we need to understand more precisely what it is, because when astronomers say they have found a structure 10 billion light-years across, they are making a claim that requires careful examination. What exactly does it mean for something to be a structure at these scales? How do we know that the clustering we observe is real and not a statistical artifact? And why does it matter which tool we use to detect it? These are not pedantic questions. They are the exact questions that other astronomers asked when Horvath's team published their findings, and the answers to them are what transformed this from an interesting anomaly into a genuine crisis for cosmology. The fundamental challenge in identifying cosmic structures is distinguishing between real physical clustering and apparent clustering that results from the way we observe the universe. Imagine you are standing in a forest at night with a flashlight that can only illuminate a limited distance. If you map all the trees you can see, the trees at the edge of your flashlight's range will appear fainter and more sparsely distributed than the trees near you, not because trees are genuinely rarer at that distance, but because your instrument loses sensitivity at the edge of its range. If you then look at your map and see a ring of sparse trees at a particular distance, you might mistakenly interpret that as a void, a real empty region in the forest, when in fact it is just the edge of your detection capability. This kind of observational artifact, called a selection effect, is one of the primary sources of false structure in astronomical surveys. A catalogue of objects built from observations of finite sensitivity will naturally show patterns that reflect the sensitivity limits of the instruments rather than the true distribution of objects in space. Any analysis of large-scale structure must carefully account for these effects. correcting for the ways in which the survey is incomplete or biased before drawing conclusions about what is real. Gamma-ray burst catalogues are particularly susceptible to selection effects. The most distant gamma-ray bursts, those at the redshifts relevant to the Hercules Corona Borealis Great Wall, are observed by satellites that have finite sensitivity and finite sky coverage. Different satellites have different detection thresholds and different pointing strategies. Some bursts occur in the direction of the Sun and cannot be observed. Others occur during satellite maintenance periods or communication gaps. The result is a catalogue that is not a perfect uniform sample of all gamma-ray bursts in the universe, but a biased, incomplete sample shaped by the operational characteristics of the instruments that detected it. Horvath's team was aware of these issues and attempted to account for them in their analysis. They examined whether the apparent clustering in the direction of Hercules and Corona Borealis could be explained by any known selection effect. They looked for correlations between the observed clustering and satellite pointing patterns. They checked whether the overdensity aligned with any known observational bias. They ran statistical tests designed to identify artificial structure generated by incomplete sampling. And in each case, their conclusion was the same. The clustering they observed was not an artifact. It was real. Subsequent independent analyses reached similar conclusions. Other groups examined the same data using different statistical methods and found the same overdensity in the same region of the sky at the same redshifts. The structure did not go away when you looked at it differently. It did not dissolve when you corrected for known biases. It persisted stubbornly in the data. This persistence is important. In the history of cosmological anomalies, many apparent discoveries have faded when subjected to more rigorous analysis, when selection effects were better understood, when larger datasets provided more statistical power, when independent teams applied fresh eyes to the problem. The Hercules Corona Borealis Great Wall has not faded. Each subsequent examination has confirmed its existence, even as debates continue about its precise boundaries and exact dimensions. The structure is there. The question is what to make of it. Now consider what the existence of this structure implies about the universe we live in and the framework we use to describe it. To do that, you need to understand a principle that sits at the absolute foundation of modern cosmology. A principle so deeply embedded in our thinking about the universe that most cosmologists treat it less as a hypothesis to be tested and more as a bedrock assumption to be relied upon. It is called the cosmological principle, and the Hercules Corona Borealis Great Wall is, depending on how seriously you take it, either a serious challenge to this principle or its outright refutation. The cosmological principle states that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. Together, these properties mean that no matter where in the universe you are standing and no matter which direction you look, you will see the same large-scale distribution of matter and energy. There is no special location in the universe. There is no special direction. At large enough scales, every patch of the cosmos looks like every other patch. This is not merely a philosophical preference for elegance and simplicity, though there is certainly an element of that. The cosmological principle is justified by observation. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire sky, we find that it is uniform to 1 part in 100,000. The temperature of this radiation is the same in every direction we look, to extraordinary precision. When we map the distribution of galaxies across large regions of the sky, we find that the overall density is consistent from one region to another, at least at the scales we have reliably mapped. The universe does appear to be homogeneous and isotropic when you zoom out far enough, but how far is far enough? This is the question that the Hercules Corona Borealis Great Wall forces us to confront. The cosmological principle is not expected to hold at small scales. Of course, individual galaxies are denser than the voids between them. Of course, galaxy clusters are denser than the surrounding cosmic web. Of course, there are filaments and walls and voids at scales of hundreds of millions of light years. All of that is expected, understood, and consistent with the principle, because the principle does not claim that every small patch of the universe looks identical. It claims that when you average over large enough regions, the distribution smooths out and becomes uniform. The scale at which this smoothing is expected to occur, the scale above which the universe should look essentially the same everywhere, is what cosmologists call the scale of homogeneity. Below this scale, structure is expected and observed. Above this scale, uniformity is expected and, according to our models, observed. Based on galaxy surveys and the predictions of our best cosmological simulations, the scale of homogeneity is estimated to be roughly 300 million light-years. Above 300 million light-years, on average, any region of the universe should look like any other region. The cosmic web still exists at those scales, but its peaks and valleys should average out. Dense regions and empty regions should balance each other. The universe should be, to a good approximation, smooth. The Hercules Corona Borealis Great Wall is 10 billion light-years across. It is more than 30 times larger than the scale of homogeneity. It is a feature, a coherent, non-uniform structure, at a scale where the cosmological principle demands uniformity. If it is what it appears to be, then the universe is not homogeneous at the scales where our models say it must be. And if the universe is not homogeneous at those scales, then the cosmological principle is not merely approximately correct with some large-scale exceptions. It is wrong in a way that undermines the mathematical foundation of the entire standard model of cosmology. The standard model of cosmology, which goes by the somewhat intimidating name lambda cold dark matter, is the most successful scientific model in the history of our species in terms of the sheer range of phenomena it correctly predicts and describes. Lambda refers to the cosmological constant, a term that Einstein introduced into his equations of general relativity to represent the energy of empty space, what we now call dark energy, the mysterious, repulsive force that is driving the accelerating expansion of the universe. Cold dark matter refers to the dominant form of matter in the universe, a type of matter that does not interact with light in any way we can directly detect, that passes through ordinary matter without interacting with it, but that nonetheless has gravitational mass, and therefore shapes the distribution of galaxies and structures across the cosmos. This model, built on these two mysterious components whose fundamental nature we do not understand, despite their dominant role in the universe's composition and evolution, makes predictions that match observation across an extraordinary range of scales and epochs. It correctly predicts the temperature of the cosmic microwave background. It correctly predicts the slight variations in that temperature across the sky. It correctly predicts the abundances of light elements produced in the first minutes after the Big Bang. It correctly predicts the rate at which the universe is expanding. It correctly predicts the distribution of galaxies at scales up to roughly 1 billion light-years, where our surveys have been comprehensive enough to test it thoroughly. It correctly predicts the formation and growth of galaxy clusters. It is not a model that has survived through lack of scrutiny. It has been tested by multiple independent methods using completely different kinds of observations, and it has passed every test, except, possibly, this one. The tension between the Hercules Corona Borealis Great Wall and the Lambda cold dark matter model is not a tension that can be resolved by adjusting a parameter or introducing a small correction. It is a tension that strikes at the model's core assumptions. And, to appreciate the depth of that tension, you need to understand something about how the model makes its predictions, specifically how it calculates the maximum size of structures that gravity can build in a universe of a given age. The calculation begins with the physics of the early universe. In the first hundreds of thousands of years after the Big Bang, the universe was so hot and dense that matter and radiation were locked together in a single fluid, a plasma, in which photons, the particles of light, were constantly scattering off electrons, unable to travel freely in any direction. In this state, gravity and radiation pressure were in constant competition. Gravity tried to pull matter together into dense clumps. Radiation pressure, the outward push of all those trapped photons, resisted the compression and pushed matter back outward. The result was oscillation. Regions of slight overdensity would begin to collapse under gravity, compress the radiation matter fluid, build up pressure, then bounce back outward, then begin to collapse again. These oscillations, called baryon-acoustic oscillations, propagated through the early universe like sound waves propagating through air, ripples in the density of the cosmic fluid moving outward from every point of original overdensity at roughly half the speed of light. Then, approximately 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons could finally combine with protons to form neutral hydrogen atoms, a transition called recombination. The moment neutral atoms formed, the photons were no longer scattered by free electrons. They decoupled from the matter and streamed freely through space for the first time. We see those photons today as the cosmic microwave background, but their departure had a profound consequence for the structure of matter. Without the radiation pressure that had been supporting the oscillating fluid, the sound waves stopped propagating. They froze in place, and the maximum distance that any sound wave had travelled from its origin point since the Big Bang until the moment of recombination became a fixed scale permanently imprinted in the distribution of matter. That scale, called the sound horizon, is approximately 490 million light-years in today's universe, accounting for the expansion that has occurred since recombination. It shows up as a subtle preferred separation distance between galaxy pairs, a slight statistical excess of galaxy pairs separated by roughly 490 million light-years compared to somewhat larger or smaller separations. This feature has been detected in multiple galaxy surveys, and its measurement provides one of the most precise tests of the standard cosmological model available. The agreement between the predicted and observed sound horizon scale is one of the model's greatest triumphs. But the sound horizon is not the limit on structure size. It is a preferred scale, not a maximum scale. Structures larger than the sound horizon can and do form as gravitational collapse continues after recombination, organizing matter into ever larger assemblies over billions of years. The question is how large those structures can grow given the finite age of the universe and the competing influence of dark energy, which at late cosmic times begins to dominate the energy budget of the universe and drives accelerating expansion that works against gravitational collapse, effectively placing a ceiling on how large structures can grow by stretching space faster than gravity can pull matter together across large distances. When you run this calculation carefully, accounting for the growth rate of perturbations in the matter distribution, the expansion history of the universe, and the suppressing effect of dark energy on late-time structure growth, you arrive at a maximum coherent structure scale of roughly 1.2 billion light-years. This is not a sharp cutoff, but rather a scale above which the probability of finding a connected overdense region falls off extremely rapidly. Structures approaching 1.2 billion light-years are rare. Structures at 2 billion light-years would be extraordinarily rare. Structures at 5 billion light-years would be so improbable that you would not expect to find even one in the entire observable universe. And a structure at 10 billion light-years is not merely improbable. Under the Standard Model, it is effectively impossible. So either the Standard Model is wrong, or the Hercules Corona Borealis Great Wall is not quite what it appears to be, or both of these things are simultaneously true in ways that we do not yet fully understand. This is where the scientific debate currently stands, and it is a debate worth following carefully because its resolution, whenever it comes, will reshape our understanding of the cosmos in ways that are difficult to predict, but impossible to overstate. Let us consider the skeptical position first, because science demands it, and because the history of cosmological anomalies counsels humility. The skeptical case against the Hercules Corona Borealis Great Wall as a single, coherent structure rests on several arguments, each of which deserves serious consideration. The first argument is about the nature of the tracer being used. The structure was detected through the distribution of gamma-ray bursts, not through a direct survey of galaxies. Gamma-ray bursts, for all their extraordinary brightness, are rare events. The catalogue used in Horvath's analysis contained hundreds of bursts across the entire observable universe. The number of bursts whose positions contributed to the identification of the Hercules Corona Borealis Great Wall was in the dozens, perhaps the low hundreds depending on how you define the structure's boundaries. Dozens of data points spread across a volume measuring billions of light-years in each dimension is an extraordinarily sparse sample. The concern is whether such a sparse sample can reliably trace the underlying matter distribution, or whether the apparent clustering could reflect clustering in the gamma-ray burst rate itself rather than clustering in the underlying large-scale structure of matter. Gamma-ray bursts are not perfectly uniform tracers of matter. They prefer certain types of galaxies over others. Long gamma-ray bursts, which make up the majority of the catalogue, occur preferentially in galaxies with low metallicity, meaning galaxies whose stars contain relatively small amounts of elements heavier than hydrogen and helium. In the early universe, at the redshifts relevant to the Hercules Corona Borealis Great Wall, most galaxies had lower metallicity than typical galaxies today, so this bias is less severe at those epochs, but it is not zero. If the low metallicity galaxy population is itself clustered in a way that does not faithfully trace the overall matter distribution, the gamma-ray burst catalogue could show apparent large-scale clustering that reflects this astrophysical bias rather than an underlying physical structure. The second skeptical argument is about the statistical methodology used to identify the structure. Different statistical techniques for identifying and characterizing large-scale structure can give different results when applied to sparse, possibly biased catalogues. The specific method used to define the boundaries and measure the size of the Hercules Corona Borealis Great Wall involves choices about what counts as a connected region, what threshold of overdensity defines the boundary of the structure, and how to handle the edges of the survey region. Different reasonable choices can give meaningfully different size estimates, and the uncertainty in the structure's true extent is larger than the headline number of 10 billion light-years might suggest. The third skeptical argument is more philosophical but no less important. Large astronomical surveys of enormous volumes contain enormous numbers of independent regions. Even if the probability of finding a structure of a given size in any particular region of the universe is very small, if you search enough regions, you will eventually find something large by pure chance. The question is whether the right comparison to make is the probability of finding such a structure in a specific, pre-designated volume, or the probability of finding it anywhere in the entire observable universe across all the surveys ever conducted. The latter probability is much higher, and critics argue that some of the statistical significance claimed for the Hercules Corona Borealis Great Wall may reflect this look elsewhere effect. Horvath and his colleagues have engaged seriously with each of these criticisms. They have argued that their statistical corrections adequately account for the look elsewhere effect, that the gamma-ray burst tracer bias at the relevant redshifts is insufficient to explain the observed clustering, and that the structure's overdensity is robust to reasonable variations in the statistical methodology. The scientific community has not reached consensus on whether these responses are fully adequate, and the debate continues in the literature with genuine uncertainty about the final verdict. But here is what makes the Hercules Corona Borealis Great Wall impossible to simply dismiss and walk away from. Even granting every reasonable skeptical argument, even accepting that the true size of the structure may be somewhat smaller than 10 billion light-years, even acknowledging that the statistical methodology has room for improvement and the tracer biases are imperfectly corrected, you are still left with something that does not fit comfortably in the standard cosmological framework. The structure is not a borderline case. It is not sitting at the edge of what the model can accommodate. It is so far outside the expected range that you would need the skeptical arguments to be almost entirely correct. You would need the apparent structure to be almost entirely an artifact with very little underlying physical reality for the standard model to escape challenge. And the independent confirmations of the structure's reality make that level of skepticism difficult to sustain. So let us take seriously the possibility that the Hercules Corona Borealis Great Wall is real. Let us ask what it would mean for our understanding of the universe if this structure genuinely exists as a coherent overdensity spanning 10 billion light-years. What explanations are available? What would have to be true about the cosmos for this structure to exist? The first category of explanation involves modifications to our understanding of the early universe, specifically to the nature of the primordial density fluctuations that seeded all structure. In the standard model, these fluctuations are described as a particular kind of random field with specific statistical properties, a so-called scale-invariant or nearly scale-invariant Gaussian random field. These properties are predicted by the theory of cosmic inflation, a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, which stretched quantum fluctuations from subatomic to cosmic scales and imprinted them as the seeds of structure. The statistical properties of these fluctuations have been measured with remarkable precision through the cosmic microwave background, and they match the inflationary predictions extremely well across a wide range of scales. But inflationary models are not unique. There are many different versions of inflation differing in the details of the physics driving the exponential expansion, and some versions predict deviations from perfect scale invariance or Gaussianity at particular scales. If the primordial fluctuation spectrum had enhanced power at scales corresponding to the Hercules Corona Borealis Great Wall, there would have been a larger than expected seed for structure at that scale, which could potentially allow gravity to build a larger structure than the standard model predicts. This kind of non-standard inflationary spectrum would be a modification of the model's initial conditions rather than its dynamics, and it would need to be consistent with all the existing observations of the cosmic microwave background that constrain the primordial spectrum so tightly. The second category of explanation involves modifications to the dynamics of structure growth, specifically to the properties of dark matter or dark energy. Dark matter, the dominant form of matter in the universe, is assumed in the standard model to be cold, meaning that its constituent particles were moving slowly compared to the speed of light at the time when structure began to form. Cold, dark matter clusters efficiently on small scales, seeding the formation of galaxies and galaxy clusters, and its properties match a wide range of observations very well. But if dark matter were not perfectly cold, if it had some residual velocity dispersion or interacted with other particles in subtle ways, the growth of structure could be modified in ways that might, in principle, allow larger structures to form than the cold, dark matter model predicts. Dark energy presents another avenue for modification. The cosmological constant, lambda, is the simplest possible form of dark energy, a fixed energy density of empty space that does not vary with time or position. But observational evidence allows for forms of dark energy that are not constant, that evolve over cosmic time, that might have been weaker in the past than they are today, which would have allowed gravity to act more efficiently over longer timescales and build larger structures than the standard model permits. Distinguishing between a true cosmological constant and an evolving dark energy is one of the primary goals of current and future cosmological surveys, and the existence of structures like the Hercules Corona Borealis Great Wall provides additional motivation for pursuing that distinction aggressively. The third category of explanation is the most radical and the most philosophically consequential. It involves questioning not just the details of the standard model, but its foundational assumption, the cosmological principle itself. What if the universe is not homogeneous at large scales? What if the distribution of matter across the cosmos is genuinely non-uniform at scales far larger than our models assume, meaning that the cosmological principle is not merely an approximation that breaks down at some very large scale, but a fundamentally incorrect description of the universe we actually inhabit? This possibility has been discussed in theoretical cosmology for decades, but it has historically been treated as a fringe position, a heretical suggestion that most cosmologists were unwilling to take seriously because the cosmological principle is so deeply embedded in the structure of our models, and because the observational evidence for large-scale homogeneity, while not perfect, has always seemed adequate to justify the assumption. But the accumulation of large-scale anomalies, of which the Hercules Corona Borealis Great Wall is the most dramatic, but not the only example, has gradually shifted the conversation. More cosmologists are now willing to ask in print and at conferences whether the universe might be genuinely inhomogeneous at scales we had assumed were safely above the homogeneity threshold. If the cosmological principle is wrong, the implications cascade through every aspect of cosmology. The mathematical framework of general relativity that we use to describe the large-scale universe assumes homogeneity and isotropy in its most fundamental equations. The Friedmann equations, which describe the expansion of the universe as a whole and which underlie every calculation of cosmic distances, ages, and evolution, are derived explicitly from the assumption that the universe is the same everywhere. If the universe is not the same everywhere at large scales, these equations are not correct descriptions of the actual cosmos. They might be good approximations in some regions, just as Newtonian gravity is a good approximation of general relativity in weak gravitational fields, but they would not be the fundamental truth. We would need a different mathematical framework, one that can describe a genuinely inhomogeneous cosmos. And deriving that framework while keeping it consistent with all existing observations would be an enormous intellectual undertaking. Some theorists have begun that undertaking. There is a body of work exploring what are called inhomogeneous cosmological models, solutions to Einstein's equations of general relativity that do not assume homogeneity or isotropy from the outset. These models are mathematically more complex than the standard framework and harder to work with, but they exist, and they make different predictions for things like the observed expansion rate of the universe and the apparent distances to faraway objects. Intriguingly, some researchers have argued that the apparent accelerating expansion of the universe, the observation that led to the discovery of dark energy, might be at least partly an artifact of living in an inhomogeneous universe where the local region we inhabit happens to be less dense than the cosmic average. In a universe with genuine large-scale inhomogeneities, an observer in a local underdensity would observe distant supernovae to be fainter than expected, which looks exactly like accelerating expansion, even if the actual expansion rate is not accelerating at all. If this interpretation were correct, dark energy might not be a physical substance filling all of space, but an illusion created by our position in a lumpy, non-uniform cosmos. This remains a minority view, and it faces substantial challenges from independent lines of evidence that support dark energy's reality. But it illustrates how deeply the question of large-scale homogeneity is entangled with some of the most fundamental open questions in cosmology. You cannot pull on this thread without unraveling pieces of the larger fabric. There is a fourth possible explanation for the Hercules Corona Borealis Great Wall that sits in a different conceptual category from the previous three. It does not require modifying the early universe or the properties of dark matter or the nature of dark energy or the cosmological principle. Instead, it asks whether the structure we are observing might be a projection effect, a structure that appears connected in 3 dimensions but is actually composed of multiple, separate structures that happen to be aligned along our line of sight in a way that makes them look like a single entity. This is not as implausible as it might sound. The universe does contain genuine large-scale structures at scales of hundreds of millions to roughly 1 billion light-years. If several such structures happen to be arranged in a chain or sheet, extending away from us along our line of sight, their individual overdensities might blend together in the redshift distribution we observe, creating what looks like a single enormous structure, but is in fact a series of distinct structures arranged end to end. The challenge with this explanation is that the apparent coherence of the Hercules Corona Borealis Great Wall is not just along the line of sight, but across the plane of the sky as well. The overdensity is extended in angular terms, covering a substantial patch of the sky in the directions of Hercules and Corona Borealis. A pure line-of-sight projection effect would produce an elongated structure primarily stretched away from us rather than a broad, roughly equidimensional overdensity. The data do not strongly support the projection explanation, but neither have they definitively ruled it out, and it remains a live possibility that improved surveys might be able to test directly. What all of these possible explanations share is that none of them is comfortable. Each requires either a significant modification of our best cosmological model or a favorable arrangement of coincidences that stretches plausibility. The Hercules Corona Borealis Great Wall does not have a clean explanation waiting in the wings. It is a genuine puzzle, the kind of puzzle that in the history of science has sometimes resolved neatly into a small correction to existing theory and has sometimes resolved into an entirely new framework that changes everything. To appreciate which of these outcomes is more likely here, it is worth looking at the history of cosmological anomalies and asking what we can learn from the cases where anomalies resolved into minor corrections and the cases where they did not. Because the history of this field is, in a very real sense, a history of anomalies, a history of observations that did not fit the prevailing model, and whose resolution ultimately revealed something profound about the nature of reality. The discovery of the expansion of the universe was itself a resolution of an anomaly. The static universe model of the late 19th and early 20th centuries, in which the cosmos was eternal and unchanging, made a prediction. The prediction was that the sky at night should be uniformly bright because in an infinite eternal static universe filled with stars, every line of sight would eventually terminate on the surface of a star, and the sky should be blazing with light in every direction. But the night sky is dark. This paradox, known as Olbers's paradox, was an anomaly for the static universe model. And its resolution came when we understood that the universe is not static, but expanding, and that the expansion redshifts the light from distant stars into invisibility. The anomaly, properly investigated, revealed the expansion of the universe. The discovery of dark matter followed a similar pattern. In the 1930s, an astronomer named Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found that they were moving far too fast for the visible matter in the cluster to hold them together gravitationally. By rights, the galaxies should have been flying apart, escaping the cluster at the speeds he measured, but they were not escaping. They were bound. The anomaly was the mismatch between the visible mass and the dynamical mass required for stability. The resolution, confirmed by decades of subsequent observation, was that the cluster contained far more mass than was visible, a form of matter that did not emit or absorb light. Dark matter. An anomaly that seemed like it might be a measurement error or a minor correction to existing models turned out to be the discovery of the dominant form of matter in the universe. The discovery of dark energy followed the same pattern at even larger scales. In the late 1990s, two independent teams of astronomers were measuring the distances to Type 1a supernovae at various redshifts to determine the expansion history of the universe. Both teams expected to find that the expansion was slowing down over time, decelerating under the mutual gravitational attraction of all the matter in the cosmos. Instead, both teams found the opposite. The distant supernovae were fainter than expected, meaning they were farther away than the decelerating universe model predicted, meaning the expansion was not slowing down. It was speeding up. The universe was accelerating in its expansion, driven by some form of energy pervading all of space, whose nature we still do not understand. An anomaly that seemed it might be an observational artifact turned out to be the discovery of dark energy, the dominant component of the universe's total energy budget. In each of these cases, the anomaly was real. The initial measurements were not errors. The observations were not artifacts of selection effects or statistical methodology. They were genuine signals pointing at something the prevailing model had missed, and in each case, taking the anomaly seriously, investigating it rigorously, and following its implications wherever they led, produced a transformation in our understanding of the cosmos. This history does not guarantee that the Hercules Corona Borealis Great Wall will yield a comparable transformation. Some anomalies do turn out to be artifacts. Some apparent discoveries do dissolve under closer scrutiny. The history of science also contains examples of exciting anomalies that were ultimately explained by mundane causes, selection effects, calibration errors, statistical flukes. We cannot know in advance which category the Hercules Corona Borealis Great Wall falls into, but the history of cosmological discovery does tell us that dismissing uncomfortable anomalies without rigorous investigation is a strategy that has consistently caused us to miss profound truths about the nature of reality. The correct response to an anomaly is not skepticism for its own sake, and it is not credulity for its own sake. It is investigation, careful and relentless, and open to surprise. What would rigorous investigation of the Hercules Corona Borealis Great Wall look like? What data would we need? What observations would we have to make to move from the current state of genuine scientific uncertainty to a confident verdict on what this structure is and what it means? The most direct path forward involves building a much larger and more uniform catalogue of gamma-ray bursts with measured redshifts than currently exists. The existing catalogue, containing hundreds of bursts with reliable distance measurements, is too sparse to resolve the current ambiguities. A catalogue of thousands or tens of thousands of bursts, distributed uniformly across the sky and detected by instruments with well-characterized sensitivity, would allow much more precise mapping of the overdensity, much more rigorous statistical testing of its reality and extent, and much better correction for potential selection effects and tracer biases. Such a catalogue would require either a new generation of gamma-ray telescopes with greater sensitivity and wider sky coverage than existing instruments, or a very long-time baseline of continued operation of current instruments, or ideally both. Several proposed and in-development space missions would contribute to this effort. Instruments designed to detect and localize gamma-ray bursts more precisely than current satellites, to measure their redshifts more reliably through rapid follow-up observations, and to achieve broader and more uniform sky coverage would dramatically improve our ability to map the large-scale structure of the universe at the redshifts relevant to the Hercules Corona Borealis Great Wall. These missions are not specifically designed to resolve this particular anomaly, but their data would be directly applicable to it. A complementary approach involves using other tracers of large-scale structure at the relevant redshifts. Quasars, the brilliantly luminous cores of distant galaxies powered by supermassive black holes consuming matter at prodigious rates, are visible across the same cosmic distances as gamma-ray bursts and can serve as alternative traces of the underlying matter distribution if the overdensity associated with the Hercules Corona Borealis Great Wall is a real physical structure. It should be detectable not just in the gamma-ray burst distribution, but also in the quasar distribution at the same redshifts and in the same sky region. Surveys of quasar clustering at these redshifts using data from instruments like the Dark Energy Spectroscopic Instrument or its successors could provide an independent confirmation or refutation of the structure's existence. Agreement between the gamma-ray burst and quasar distributions would be powerful evidence for reality. Disagreement would point toward a tracer-specific artifact. There is also the possibility of detecting the Hercules Corona Borealis Great Wall through its gravitational effects, rather than through the distribution of objects within it. A structure of this scale, if it contains the amount of mass implied by its size and the density contrast implied by the overdensity of gamma-ray bursts, would exert measurable gravitational influence on the light passing through and around it. Gravitational lensing, the bending of light by massive objects predicted by general relativity, operates at all scales from individual stars to galaxy clusters to the largest structures in the cosmic web. A structure 10 billion light-years across containing a significant overdensity of matter would produce a weak but potentially detectable lensing signal in the shapes of background galaxies seen through it. Measuring this signal would require exquisite precision in galaxy shape measurements across a large patch of sky, but next-generation survey telescopes are designed to achieve exactly this kind of precision. If the lensing signal in the direction of Hercules and Corona Borealis at the appropriate redshift is detected and matches what would be expected from a genuine large-scale overdensity, the case for the structure's reality becomes essentially airtight. The cosmic microwave background offers yet another window. The distribution of matter along the line of sight between us and the last scattering surface, where the cosmic microwave background photons were last scattered before streaming freely, affects the temperature pattern of the background through a process called the integrated Sachs-Wolf effect. When cosmic microwave background photons pass through an overdense region of the universe, they gain a slight amount of energy as they fall into the gravitational potential well of the overdensity, and they lose a slight amount of energy as they climb back out. In a universe with a cosmological constant, these two effects do not exactly cancel, because the potential well is decaying as dark energy drives accelerating expansion, and the net result is a slight warming of the cosmic microwave background photons that passed through the overdensity. A structure as massive as the Hercules Corona Borealis Great Wall would produce an integrated Sachs-Wolf signal that could, in principle, be detected by correlating the cosmic microwave background temperature map with the spatial distribution of the structure. The signal would be subtle, but it would provide a completely independent line of evidence bearing on the structure's reality and mass. Each of these approaches, better gamma-ray burst catalogues, quasar surveys, weak gravitational lensing, cosmic microwave background correlations, represents a different physical observable that would respond to the presence of a genuine large-scale overdensity. If multiple independent probes all confirm the overdensity at the same location and redshift, the convergence of evidence would be overwhelming. If they give conflicting results, that conflict would itself be informative, pointing toward specific kinds of artifacts or systematic errors that could then be investigated and corrected. Science advances most reliably not through single decisive experiments, but through the accumulation of independent lines of evidence that either converge on a consistent picture or reveal inconsistencies that point towards something previously unrecognized. The next decade of astronomical observation will provide much of this data. We are living through what astronomers call a golden age of survey science, a period in which multiple large-scale instruments are coming online simultaneously, each designed to map the universe with unprecedented precision and depth across complementary wavelengths and physical probes, the Vera-C. Rubin Observatory in Chile, with its enormous field of view and its ability to image the entire southern sky repeatedly over a decade, will produce a catalogue of billions of galaxies with measured shapes and photometric redshifts, enabling weak lensing studies of extraordinary precision. The Euclid mission, a European Space Agency satellite launched in 2023, is conducting a spectroscopic survey of hundreds of millions of galaxies across a large fraction of the sky, providing precise three-dimensional maps of the galaxy distribution at cosmic distances relevant to the Hercules Corona Borealis Great Wall. The Dark Energy Spectroscopic Instrument at the Kitt Peak National Observatory in Arizona is already collecting spectra of tens of millions of galaxies and quasars, building a three-dimensional map of the universe at redshifts that partially overlap with the structure's location. None of these instruments was designed specifically to resolve the mystery of the Hercules Corona Borealis Great Wall. They were designed to address fundamental questions about dark energy, dark matter, and the expansion history of the universe. But their data will inevitably bear on this mystery because those fundamental questions and this particular anomaly are deeply entangled. If the structure is real and reflects a genuine violation of the cosmological principle, then the measurements of the expansion rate, the growth rate of structure, and the statistical properties of the matter distribution that these instruments are designed to make will all show inconsistencies with the Standard Model's predictions, inconsistencies that might already be hiding in the data at the level of current measurement precision, and that will become unmistakable as precision improves. There is something deeply clarifying about understanding the stakes of this observational program. We are not merely trying to resolve a debate about whether a particular cluster of gamma-ray bursts constitutes a genuine physical structure or a statistical artifact. We are asking whether the foundation of our entire cosmological framework is correct. We are asking whether the universe we live in is the universe described by our best models, or whether there is something fundamental about the cosmos that we have misunderstood at the deepest level. The answer to that question, whatever it turns out to be, will reshape not just cosmology but physics more broadly, because the cosmological principle and its mathematical consequences extend throughout theoretical physics in ways that reach far beyond the study of large-scale structure. Consider what it would mean for physics if the cosmological principle were genuinely violated at scales of 10 billion light-years. It would mean that our mathematical description of the universe, the one we have been using for a century, the one that underlies our calculations of everything from the age of the universe to the distances to remote galaxies to the conditions in the early universe, is built on an incorrect foundation. Every cosmological measurement we have ever made has been interpreted within the framework of a homogeneous universe. The precise values we have derived for fundamental cosmological parameters, the expansion rate, the density of matter, the density of dark energy, the spectral index of primordial fluctuations, all of these were extracted from observations using mathematical tools that assume homogeneity. If the universe is not homogeneous at the scales we assumed, the extraction of these parameters was not fully correct, and the values we have derived may not accurately reflect the true properties of the cosmos. We would have to go back and redo the analysis in the context of a more accurate framework, and the parameter values might shift in ways that resolve some of the tensions that currently exist in cosmology, or might introduce new ones that point toward even deeper problems. One of the most discussed tensions in contemporary cosmology is what has become known as the Hubble tension. Different methods of measuring the current expansion rate of the universe, the Hubble constant, give different answers that are inconsistent with each other at a level of statistical significance that has grown too large to comfortably attribute to measurement error. Measurements based on the cosmic microwave background, using the standard model to extrapolate from the early universe to today, give a Hubble constant of approximately 67 kilometers per second per megaparsec. Measurements based on the cosmic distance ladder, using Cepheid variable stars, and Type 1a, a supernovae, to directly measure distances and recession velocities of nearby and moderately distant galaxies, consistently give a value of approximately 73 kilometers per second per megaparsec. These two numbers disagree by approximately 9%, and the disagreement has persisted and strengthened as measurements have become more precise. It is not going away. Various explanations have been proposed for the Hubble tension, ranging from unidentified systematic errors in one or both measurement methods to genuine new physics beyond the standard model involving early dark energy, interacting dark matter, or modifications to the behavior of gravity. The possibility that the tension reflects a genuine large-scale inhomogeneity in the universe, with our local region having a slightly different expansion rate than the cosmic average assumed by the standard model, is among the explanations that have been seriously considered. If the Hercules Corona Borealis Great Wall indicates that the universe is genuinely inhomogeneous at very large scales, then the assumption that our local measurements of the expansion rate should agree with a globally averaged value derived from the cosmic microwave background might itself be flawed. We might be measuring different things without realizing it, because the standard model's assumption of homogeneity causes us to conflate local and global quantities that are actually distinct in the real universe. The Hubble tension and the Hercules Corona Borealis Great Wall anomaly are not obviously the same problem. They involve different scales, different observations, and different aspects of the standard model. But they are both symptoms of a possible deeper issue with the cosmological framework, and there is at least a plausible conceptual connection between them. A universe that violates the cosmological principle at the scales implied by the Great Wall might also exhibit local variations in the expansion rate of the kind that could explain the Hubble tension. Whether this connection is real, whether the same fundamental departure from the standard model could simultaneously explain both anomalies, is a question that current theory cannot definitively answer, but that future observations and theoretical work might be able to address. There is something almost vertiginous about tracing these implications. We began with a cluster of violent explosions in a particular patch of the distant sky, a statistical overdensity in a catalogue of gamma-ray bursts, an anomaly that might seem like an obscure technical detail in the margins of observational cosmology. And we have followed the thread of that anomaly upward through layers of implication until we find ourselves confronting questions about the foundations of physics, the correctness of our measurements of fundamental constants, and the possibility that the universe we thought we understood is constructed differently at its largest scales than anything our models describe. This is how science works at its most productive and most unsettling. A single, stubborn fact, properly examined, can unravel the most carefully constructed understanding. We should also take a moment to appreciate the sheer audacity of the enterprise that produced this discovery. Human beings living on a small rocky planet orbiting an unremarkable star in one of hundreds of billions of galaxies, using instruments that fit within the confines of a satellite no larger than a school bus, detected the faint flickers of catastrophic stellar explosions occurring 10 billion light-years away in the first third of cosmic history, and used the pattern of those flickers to map the largest known structure in the observable universe. The instruments, the mathematics, the astrophysics, and the cosmological framework that made this possible represent the accumulated intellectual achievement of thousands of scientists working across generations, building on each other's discoveries, refining each other's techniques, correcting each other's errors, in a collective endeavor that has no parallel in human history for its ambition or its scope. That the result of this endeavor is an anomaly, a discovery that does not fit the model rather than one that confirms it, is not a failure. It is the system working exactly as it should. Science does not advance by finding what it expects. It advances by finding what it does not expect, by being honest about the discrepancy between prediction and observation, and by following the implications of that discrepancy wherever they lead, even when they lead somewhere uncomfortable. The discomfort is real, and it is worth sitting with for a moment before we continue. Because there is a particular kind of intellectual discomfort that cosmologists face when confronting anomalies like the Hercules Corona Borealis Great Wall, a discomfort that goes beyond the ordinary scientific challenge of explaining an unexpected observation. It is the discomfort of potentially having to abandon a framework that has served extraordinarily well, that has been tested rigorously and repeatedly, that has produced precise and accurate predictions across an enormous range of phenomena, and that underlies not just cosmology, but much of theoretical physics. Abandoning such a framework, or even seriously entertaining the possibility of abandoning it, requires a particular kind of intellectual courage that is easy to underestimate from the outside. Scientists are human beings. They have careers built on the existing framework. They have spent decades mastering its mathematics, its predictions, its subtleties. They have used it to make discoveries, to train students, to write papers that have shaped the field. The prospect that the foundation of all that work might be incorrect is not abstract. It is personal. It threatens not just a theory, but an entire way of understanding the world, an entire professional identity. The history of science is full of examples of brilliant people who could not make the psychological leap required to abandon a framework they had devoted their lives to, even when the evidence against it became overwhelming. And it is also full of examples of brilliant people who made that leap too eagerly, who abandoned solid frameworks prematurely on the basis of anomalies that ultimately turned out to be artifacts. The challenge is knowing which situation you are in, and that knowledge is rarely available in advance. What we can say with confidence is that the cosmological community is taking the Hercules Corona Borealis Great Wall seriously. It is being discussed in the technical literature with genuine engagement rather than dismissal. Groups around the world are working on the improved observations and more sophisticated analyses that could resolve the question of its reality and its implications. Theoretical cosmologists are exploring what kinds of models could accommodate a structure of this scale without violating other well-established observations. This is exactly the response that a genuine anomaly deserves, and it suggests that whatever the ultimate verdict on this particular structure, The process of investigating it is already producing valuable scientific work. Now, we should turn from the sociology of science to a deeper question, one that the Hercules Corona Borealis Great Wall forces us to confront, even if it ultimately turns out to be entirely explicable within the existing framework. That question is this: what does the existence of structure at these scales tell us about the nature of the universe we inhabit and our relationship to it? To approach this question honestly, we need to think carefully about what it means to observe the universe from a single point in space and time, which is the only vantage point any observer has ever occupied or ever will occupy. We observe the cosmos from Earth, from a specific location in the Milky Way, at a specific moment in cosmic history. Our observations are necessarily shaped by this vantage point in ways that are sometimes easy to correct for and sometimes subtle and difficult to fully account for. The light we receive from distant objects left those objects in the past, and the further away an object is, the further back in time we are seeing it. When we observe the Hercules Corona Borealis Great Wall, we are not seeing what is there now. We are seeing what was there when the universe was between roughly 1/3 and 1/2 of its current age. Whatever we observe is a snapshot of the past, and inferring the present state of the cosmos from that snapshot requires theoretical assumptions about how things evolve, assumptions drawn from the very framework that the anomaly challenges. This is not a trivial problem. The observable universe is a sphere centered on Earth, bounded by the cosmic horizon, the distance beyond which light has not had time to reach us since the Big Bang. Everything we know about the cosmos comes from within this sphere. Everything outside it is, by definition, unobservable, and will remain so forever, because the expansion of the universe is causing the horizon to recede faster than light can cross the increasing distance to the edge. The observable universe is not the whole universe. It is a finite patch of a possibly infinite cosmos, and there is no guarantee that what we observe within our horizon is representative of what lies beyond it. The cosmological principle in its most ambitious form is a claim not just about the observable universe, but about the universe as a whole. It says that the cosmos is homogeneous and isotropic everywhere, not just in the patch we can see. This claim is not testable in the strict sense. We cannot observe beyond our horizon. We cannot check whether the universe is the same on scales larger than the observable cosmos. We can only observe what is within our horizon and ask whether it is consistent with homogeneity, which is a much weaker test. The fact that our observable universe appears roughly homogeneous at scales up to a few 100 million light-years does not prove that the universe is homogeneous at all scales, or beyond the horizon, or in any deeper sense. It only tells us that within the limited patch we can see, the distribution of matter is approximately uniform at the scales we have reliably mapped. The Hercules Corona Borealis Great Wall, if real, is telling us that even within our observable patch, the homogeneity we assumed breaks down at scales much larger than we thought. And if homogeneity breaks down within the observable universe at scales of 10 billion light-years, what confidence can we have that the universe beyond our horizon is more uniform? The honest answer is very little. The observable universe might be an atypical patch of a much larger cosmos with profound large-scale structure, extending far beyond anything we can see. We might be living inside a region of the cosmos that happens to look approximately homogeneous at the scales we have mapped. The way a person standing in a field might see uniform grass in every direction for a kilometre, without knowing that the field is itself embedded in a landscape of mountains and valleys and oceans stretching beyond their horizon. This is an uncomfortable thought, and it has been uncomfortable in different forms for as long as people have thought carefully about cosmology. Every advance in our ability to see further has revealed structure that the previous generation of instruments could not resolve. The universe we thought was made of the solar system alone turned out to contain stars beyond counting. The universe we thought was made of stars alone turned out to contain galaxies beyond counting. The universe we thought was made of uniformly distributed galaxies turned out to have a cosmic web of filaments and voids of breathtaking complexity. At every scale where we developed the tools to look carefully, we found more structure than we expected. There is no obvious reason to believe that this pattern has stopped at the current limit of our instruments. The philosopher of science would note that there is something epistemologically vertiginous about this situation. We are using the standard cosmological model to interpret our observations of the universe, and we are using those observations to test the standard cosmological model. This circularity is not vicious in the technical, logical sense, because we are testing whether the model's predictions match new observations it was not designed to fit, rather than merely confirming observations already used to build the model. But it means that our understanding of the cosmos is always model-dependent in ways that are difficult to fully escape. When we calculate the distance to the Hercules Corona Borealis Great Wall using the measured redshifts of gamma-ray bursts, we are using the expansion history of the universe as predicted by the standard model to convert those redshifts to distances. If the standard model's expansion history is wrong in ways connected to the large-scale inhomogeneities the structure implies, then our distance estimate might itself be systematically incorrect, and the structure might be at a different distance, with a different size, than we calculate. The anomaly potentially infects the very tools we use to characterize it. This is not a counsel of despair or of radical skepticism about scientific knowledge. It is a recognition of how sophisticated and carefully circumscribed the process of building reliable cosmological knowledge actually is. Scientists understand these circularity issues and work to address them through multiple independent measurement methods, through internal consistency checks, and through the development of methods that are less sensitive to particular model assumptions. The goal is always to find observations and analyses that are as model-independent as possible. That would give the same result regardless of which reasonable cosmological framework you are using to interpret them. Progress toward this goal is real and ongoing, but it is never complete. And the Hercules Corona Borealis Great Wall is a case where the model dependence of our conclusions is particularly significant. What would it feel like to genuinely know that the universe is structured at scales far beyond what our models describe? Not just to know it as an abstract scientific conclusion, but to internalize it, to feel its weight, to let it change the texture of your understanding of where you are and what surrounds you. This is not a question with a scientific answer. It is a question about what it means to be a conscious creature, confronting the scale and structure of the cosmos. But it is not a trivial question, and it is one that the Hercules Corona Borealis Great Wall, whatever its ultimate scientific status, forces us toward with unusual urgency. We tend to think of the universe as a backdrop, a context in which things happen, a stage on which the drama of matter and energy and life plays out. We tend to think of its large-scale structure as something remote and abstract, relevant to cosmologists with their equations and their telescopes, but not to the lived experience of beings whose entire existence transpires within a tiny bubble of space around a single star. The discovery that the universe contains structures at scales of 10 billion light-years, structures whose existence challenges our best understanding of how the cosmos evolved, is not something that touches our daily lives in any practical sense. The morning is no different with or without the Great Wall. The coffee is still hot. The world still turns. But there is another way to hold this knowledge, a way that does not require it to be practically relevant in order to be deeply significant. The universe, at the largest scales we can probe, is doing something that we do not understand. It contains something that our best models say should not be there. In all of the vast computational effort we have invested in simulating the cosmos, in all of the mathematical elegance we have found in the equations of general relativity and quantum field theory, in all of the precision measurements we have assembled from decades of telescope time on mountaintops and in space, we have not managed to build a complete and consistent picture of the universe we actually inhabit. There is something out there, something enormous and ancient and stubbornly present in the data that our framework cannot account for. And that fact, that stubborn, humbling, magnificent fact, is one of the most important things we have ever discovered about our situation. The history of humanity's relationship with the cosmos is, at its deepest level, a history of recalibrating our sense of our own significance. Every major astronomical discovery has required us to revise downward our estimate of how central and special our position is. The Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. The universe has no center, or rather every point in it is equally a center, which amounts to the same thing from the perspective of any individual observer. We are not special. We are not privileged. We are not at the heart of anything. We are a mote of biology on a mote of rock, orbiting a mote of fire in one corner of an incomprehensibly vast and indifferent cosmos. This is the Copernican legacy, and it has been the dominant narrative of the scientific revolution's impact on human self-understanding. The universe is not about us. We are not its purpose. We are an accident, a local fluctuation in the distribution of matter and energy, no more cosmically significant than a particular eddy in a river or a particular grain of sand on a beach. This narrative has been enormously productive scientifically, because it encourages us to look at the universe objectively, without projecting human concerns onto its structure, without assuming that our local circumstances tell us anything general about the cosmos as a whole. It is also, in its most extreme form, deeply impoverishing as a philosophy of existence, and most thoughtful people who engage with it find themselves reaching for some way to recover a sense of meaning that the bare, scientific facts seem to have dissolved. The Hercules Corona Borealis Great Wall does something interesting to this narrative. It reinforces the smallness and insignificance of our position in the cosmos, as any discovery of enormous cosmic structure must. A structure 10 billion light-years across makes the entire observable universe feel cramped and local. It makes the distances between galaxies, those gulfs of hundreds of thousands to millions of light-years that already seemed beyond comprehension, feel almost cozy by comparison. It is a fresh application of the Copernican lesson, a reminder that no matter how large we think the relevant scales are, the universe is larger. But it also does something else. It tells us that the universe is more complex, more surprising, and more resistant to our understanding than we had hoped. It tells us that we are not close to a complete description of the cosmos. It tells us that the story of discovery is not nearly over. that the most fundamental questions about the structure and nature of the universe remain open in ways that should inspire rather than discourage. There is something to be found in this discovery that is not diminishment, but invitation. The universe is stranger and richer than our models. The map does not capture the territory. There is more to learn. This combination of smallness and open mystery is, when you hold both of them at once without flinching from either, one of the most remarkable things about being a conscious creature in this universe. We are small enough that the largest structure we have ever discovered is completely indifferent to our existence, has no relationship to us whatsoever, would be exactly as it is whether or not any conscious beings had ever evolved anywhere in the cosmos to observe it. And we are complex enough, curious enough, persistent enough that we found it anyway. We aimed our satellites at the sky. We measured the redshifts of ancient explosions. We wrote the software to analyze the patterns in the data. We argued about the statistics. We wrote the papers. We checked each other's work. And at the end of all that, we had something that no other process in the known universe has ever produced. We had knowledge of a structure 10 billion light-years across, knowledge that exists nowhere in the universe except in the minds of a small number of human beings on a small planet around an ordinary star. That is not nothing. That is, in fact, something so extraordinary that it is difficult to fully appreciate, even from the inside. The universe does not know about itself. Matter and energy do not comprehend the structures they form. The Hercules Corona Borealis Great Wall does not know it is the largest structure in the observable universe. It does not know it contradicts our models. It does not know it is called Hercules Corona Borealis, or that it was named after constellations that ancient human civilizations traced in the night sky from a planet too small to appear on any map of it. All of that knowing happens in one place, and that place is consciousness. And consciousness, as far as we know, is rare and fragile and confined to small warm pockets of biochemistry scattered here and there in the cold immensity of space. When we discover something about the universe, we are not merely adding to a database of facts. We are participating in the only process by which the universe becomes aware of itself. We are the cosmos looking back at its own structure with instruments and mathematics and curiosity. There is a philosophical tradition reaching from ancient Greek thought through Spinoza, through the German idealists, to certain strands of contemporary philosophy of mind that treats consciousness not as an accident of biological evolution, but as something fundamental to the nature of reality. Something that the universe tends toward rather than stumbles into. This tradition has always been at the margins of scientific respectability, and for good reasons, because it is difficult to formulate its central claims precisely enough to test them. But there is something about standing at the intersection of the largest known structure in the universe and the small, fragile process of human understanding that makes this tradition feel less dismissible than usual. We should also consider what the Hercules Corona Borealis Great Wall tells us about the limits of observation itself, not just our current observations, but observation in principle. The structure sits at redshifts corresponding to distances where the universe was between 1/3 and 1/2 of its current age. At those distances, the light we receive has been traveling toward us for between 7 and 9 billion years. The universe through which that light traveled was different from the universe today, less expanded, differently structured, with different average densities of matter and dark energy. The objects within the structure that produced the gamma-ray bursts we detected, the massive stars whose collapse triggered those extraordinary explosions, have long since ceased to exist. The stars burned out. The galaxies evolved. The structure itself may have dispersed or coalesced or changed in ways we cannot calculate, without knowing its precise mass and internal dynamics and the local expansion rate. What we see when we look at the Hercules Corona Borealis Great Wall is a fossil, an imprint of conditions that existed in the universe billions of years before the Earth formed, preserved in the distribution of photons that happened to travel in our direction and arrive at our instruments at this particular moment in cosmic history. This temporal displacement is a feature of all astronomical observation, not just observations of the most distant structures. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago, before modern humans had evolved. When we look at the most distant galaxies detectable with current instruments, we see them as they were less than 1 billion years after the Big Bang, when the universe was a different place entirely. Astronomy is always archaeology. The further you look, the further back in time you see. The universe we observe is not the universe as it is, but the universe as it was, at a series of different moments in its past, simultaneously visible to us because light from those moments is arriving at Earth now after journeys of different lengths. This means that our map of the universe is not a map of a single moment, but a map of many moments superimposed on each other, a palimpsest of cosmic history in which the nearby universe is seen in its current state and the distant universe is seen as it was billions of years ago. The Hercules Corona Borealis Great Wall is embedded in this map at its most ancient visible layers. It is part of the universe's past, not its present. Whether the structure still exists in some recognizable form today, whether it has grown or dispersed or merged with other structures over the intervening billions of years, is something we cannot directly observe. We can only model it, and our models, as we have seen, are precisely the tools that its existence calls into question. There is something deeply strange about this situation that goes beyond the ordinary strangeness of cosmological thinking. We are using observations of the past to test models of how the past evolved into the present. The very structure whose existence challenges our models is visible to us only because of the time delay imposed by the finite speed of light, the same finite speed that imposes the causal constraints underlying the theoretical maximum structure size. Light speed connects and limits simultaneously. It is what allows us to see the universe's history and what prevents structures from growing beyond certain scales. The tool of discovery and the constraint on the discovery are both expressions of the same fundamental constant. And there is something almost paradoxical about using one consequence of light's finite speed to identify a structure that apparently violates another consequence of that same finite speed. This is the kind of deep interconnection that appears throughout fundamental physics, the way the same principles that define the constraints we impose on the universe also define the instruments through which we observe it, so that any observation we make is always already shaped by the laws we are trying to test. We cannot step outside this entanglement. We cannot find a vantage point from which the laws of physics are not operative, from which we could observe the universe directly without our observations being filtered through the very physics we are investigating. We are inside the system we are trying to understand, and we are made of the same materials and subject to the same laws as everything else in it. Our instruments are made of atoms. Our mathematics is performed by neurons. Our telescopes operate according to the laws of optics and electromagnetism. Everything we know about the universe we know through processes that are themselves part of the universe, and this inseparability is not a methodological inconvenience to be overcome, but a fundamental feature of the epistemic situation of any embedded observer. The great physicist John Archibald Wheeler, who was among the most creative and philosophically sophisticated thinkers in the history of physics, spent the later decades of his career developing a vision of the universe he called participatory, in which the act of observation is not a passive reception of pre-existing facts, but an active participation in the constitution of reality. Wheeler's ideas were controversial and remain so, and it would be a mistake to enlist him in support of any particular interpretation of cosmological anomalies. But his central intuition that the relationship between the observer and the observed is more intimate and more philosophically significant than the naive picture of science as detached objective measurement suggests, resonates in an interesting way with the situation we are describing. We are not merely finding facts about a universe that exists independently of our looking, we are asking questions of the universe using instruments and frameworks that we built, and the answers we get are shaped by the questions we asked and the tools we used to ask them. The Hercules Corona Borealis Great Wall is an answer that does not fit the question we thought we were asking. What does it mean for an answer not to fit the question? In ordinary life, when we ask a question and receive an answer that does not fit, we assume one of two things. Either we asked the wrong question or we received a misleading answer. In science, both possibilities are always in play, and distinguishing between them is the central challenge of empirical inquiry. The history of the Hercules Corona Borealis Great Wall investigation is, in a real sense, an extended attempt to determine which of these two possibilities applies. Is the data misleading us through selection effects and statistical artifacts and tracer biases, giving us the appearance of a structure that is not really there? Or is the data telling us something true that our framework is not equipped to receive, something that the question we were asking, framed in terms of the standard cosmological model, was not designed to accommodate? The answer to this question matters enormously, not just for cosmology, but for our broader understanding of what science is and how it works. If the data is misleading us, then the lesson is about the importance of rigor, of checking and rechecking methods, of being alert to the ways in which incomplete and biased observations can produce false patterns. This is a valuable lesson, and one that the scientific community takes seriously. But it is not a revolutionary one. It is science doing what science always does, correcting itself through better data and more careful analysis. If, on the other hand, the data is telling us something true, then the lesson is about the limits of our framework, about the danger of mistaking a successful model for a complete one, about the ways in which the very power and precision of our best theories can blind us to their limitations by making everything we observe look like confirmation of what we already believed. The second lesson is the more philosophically important one, and it connects to a broader pattern that appears throughout the history of science. The most powerful and successful scientific frameworks have a way of becoming invisible. They become so thoroughly embedded in the way we interpret data, so deeply woven into the instruments and methods we use to make observations, so completely identified with the phenomena they describe, that we stop experiencing them as frameworks at all. We stop seeing them as models of reality and start seeing them as reality itself. And when this happens, anomalies that should prompt a re-examination of the framework instead get reinterpreted as measurement errors or statistical flukes, or minor puzzles that the framework will eventually absorb, because the alternative, that the framework itself is limited, has become literally unthinkable within the conceptual vocabulary the framework provides. Thomas Kuhn, the philosopher and historian of science, described this dynamic in his influential analysis of scientific revolutions. He argued that normal science, the day-to-day practice of working within an established framework, is characterized precisely by this inability to take anomalies seriously as challenges to the framework. The framework defines what counts as a valid question, what counts as an acceptable answer, and what counts as a problem worth investigating. Anomalies are initially treated as puzzles to be solved within the framework, rather than as challenges to the framework itself. Only when the anomalies accumulate to the point where they can no longer be plausibly accommodated, when the auxiliary hypotheses needed to explain them away have become so elaborate and so numerous that they constitute a more complex and less elegant framework than a direct revision of the original would be, only then does the community begin to seriously consider a paradigm shift. Kuhn's account has been criticized and refined by subsequent philosophers of science, and it should not be applied too mechanically to any specific case. But it offers a useful lens for understanding why the cosmological community has responded to the Hercules Corona Borealis Great Wall with a mixture of serious engagement and persistent reluctance to draw strong conclusions. The community is doing what Kuhn's model predicts normal science would do. It is exploring whether the anomaly can be absorbed into the existing framework through better data and more careful analysis, which is entirely reasonable given the stakes of abandoning a framework as successful as the standard model, and it is maintaining appropriate skepticism about the anomaly's implications until the evidence becomes overwhelming. Whether the evidence will become overwhelming and how quickly depends on the observational programs currently underway and those planned for the coming decade. What we can say with confidence is that the community is not complacent. The anomaly is being taken seriously as a scientific problem, and the investigations it has prompted are producing genuine knowledge regardless of how they ultimately resolve. New statistical techniques for characterizing large-scale structure in sparse catalogues are being developed. New observational programs are being designed. New theoretical work is exploring what kinds of models could accommodate structures at the relevant scales. The machine of science is engaged, and that engagement, whatever it produces, represents an advance in our understanding of the cosmos and our tools for studying it. Let us take a step back from the immediate scientific debate and consider the Hercules Corona Borealis Great Wall in the context of the universe's history as a whole, the full arc from the Big Bang to the present moment and beyond. This structure, whatever its ultimate explanation, is an object embedded in the deep past of the cosmos, a feature of the universe as it existed between 7 and 9 billion years ago. In the billions of years since the gamma-ray bursts that revealed its presence, the universe has continued to evolve. Galaxies within the structure, if they indeed constitute a coherent physical entity, have continued to form stars and merge with neighbors and feed their central black holes. The dark energy that is currently driving the accelerating expansion of the universe has continued to dilute the gravitational bonds between structures, making it increasingly difficult for gravity to maintain coherence across large scales. The structure, whatever it is now, is not what it was when we observe it. The future of large-scale structure in the universe is, in a sense, the inverse of its past. In the early universe, gravity was winning. Density fluctuations were growing, structures were forming, organizing, becoming more complex and more differentiated. The cosmic web was assembling itself from the nearly uniform plasma of the early cosmos into the intricate network of filaments and nodes and voids that we observe today. But dark energy has been accelerating the expansion of the universe for roughly the last 5 billion years. And as the universe continues to expand and dark energy continues to dominate, gravity's ability to maintain and grow large-scale structures will increasingly be overcome. The expansion of space between galaxy clusters is already proceeding faster than the clusters can gravitationally communicate with each other. On timescales of trillions of years, the universe will become an increasingly lonely place, with galaxies and galaxy groups isolated in expanding voids, separated by distances so large that even light will not be able to bridge them within any finite future time. The structures we see today in the cosmic web, the filaments and clusters and great walls, are in this sense the high water mark of cosmic organization. They represent the maximum complexity that gravity has been able to assemble before dark energy begins to irreversibly dismantle the architecture. We are living at a particular moment in cosmic history, roughly 13.8 billion years after the Big Bang, when the universe is neither too hot and dense for structure to form, nor too expanded and dark energy dominated for it to be maintained. We are in the window of maximum structural complexity, the epoch during which the cosmos is most organized, most differentiated, most capable of supporting the intricate chemistry and stable environments that give rise to life and consciousness. This is not a coincidence or a miracle. It is a consequence of the parameters of the universe we inhabit, the values of the fundamental constants, and the initial conditions of the Big Bang that together determine the timeline of cosmic evolution. But it is worth appreciating that our existence is not merely an accident of biological evolution, it is also an accident of cosmic timing. We are here in this window because if we were not in this window, we would not be here at all. The Hercules and Corona Borealis Great Wall is a feature of this window of maximum complexity. It is, if it is real, the largest structure that the universe has ever produced or ever will produce, because the conditions that allowed its formation, whatever those conditions were, have not existed since, and will not exist again as the universe continues to expand and cool and thin. It is a one-time thing, a structure unique to this particular phase of cosmic history, visible to us because we happen to exist in the same epoch and in a location from which our instruments can detect its signature in the ancient light of catastrophic stellar deaths. Its existence and our ability to detect it are both products of the same cosmic moment. There is something poignant in this realization. The universe will not always be observable. As the expansion of space accelerates, the galaxies beyond our local group, the gravitationally bound collection of a few dozen galaxies that includes the Milky Way and Andromeda, will eventually recede beyond our cosmological horizon. Their light will be redshifted to invisibility. The cosmic microwave background will cool further and further, becoming increasingly difficult to detect. The evidence that the universe had a beginning, that it evolved from a hot, dense state, that it contains the structures we observe, will gradually fade from observability. In the far future, A civilization arising in an isolated galaxy, in an otherwise empty-looking universe, would have no way to discover that it was part of a cosmos that once contained a web of filaments and clusters and great walls stretching across billions of light years. They would look out into darkness and conclude that they were alone in a static, eternal, featureless universe. The knowledge we have assembled about the structure and history of the cosmos is available to us only because we exist in this particular epoch, early enough in cosmic history that the evidence of complexity is still visible. We are not just living in the window of maximum structural complexity. We are living in the window of maximum cosmological knowledge. The observable universe is larger now, in terms of the information it contains and the structures it reveals, than it will ever be again. Every billion years, more of the universe recedes beyond our horizon. Every billion years, the evidence for the Big Bang grows fainter. Every billion years, the cosmic web becomes less coherent as dark energy drives the expansion that will eventually dissolve it. The universe is, in a real sense, forgetting itself, erasing the record of its own history as it expands. And we are alive at the moment of maximum legibility, when the record is fullest and most detailed, when the structures it contains are largest and most complex, when the instruments and mathematics and accumulated scientific knowledge exist to read that record with the greatest fidelity. This is not a perspective that diminishes the significance of what we do not know. It amplifies it. We are in the best possible position, cosmically speaking, to understand the universe, and we still have not managed to explain the largest structure we have ever found. The Hercules Corona Borealis Great Wall is a reminder of how much remains to be understood even at the moment of maximum opportunity. How deep the mystery runs even when we are looking at the clearest picture we will ever have. It is an invitation to urgency as well as to humility. Urgency and humility are not comfortable companions, they pull in different directions. Urgency says that there is much to do and limited time to do it, that the questions are pressing and the window of opportunity is finite, and the work should be prosecuted with everything we have. Humility says that we should be cautious about our conclusions, that our tools are imperfect, and our frameworks are incomplete, and the history of premature certainty is long and not flattering. The practice of science requires holding both of these orientations simultaneously, pressing forward with energy and ambition while remaining genuinely open to being wrong, investing deeply in the investigation while refusing to become so invested in a particular outcome that you can no longer see the data clearly. This is harder than it sounds. It requires a kind of disciplined intellectual character that is rare in any domain and perhaps especially difficult in one where the stakes are as high as they are in fundamental cosmology. The stakes are high because cosmology is not just one science among others. It is the science of the whole, the discipline that asks not about this phenomenon or that object, but about the totality of what exists and how it came to be and what it will become. The questions cosmology asks are the questions that human beings have always asked, long before there was science to pursue them. Where did everything come from? What is the universe made of? How large is it? How old? What is its fate? These questions have been asked by every culture in human history, answered in myths and theologies and philosophies that differ enormously in their content, but share a common impulse, the impulse to locate ourselves in a larger whole, to understand the context in which our brief existence occurs. Modern cosmology is the latest and most rigorous attempt to answer these questions, and its answers, where they exist, have transformed our understanding of our situation in ways that dwarf anything previous generations could have imagined. But the answers are incomplete. The standard cosmological model, for all its extraordinary power and precision, is a framework built on two foundations that we do not understand. We do not know what dark matter is. We have inferred its existence from its gravitational effects. We have mapped its distribution across the cosmos. We have constrained its properties through dozens of independent observations, but we have never directly detected a single dark matter particle. Every experiment designed to catch dark matter in the act of interacting with ordinary matter has come up empty. Decades of searching in deep mines shielded from cosmic rays, in particle colliders smashing matter at enormous energies, in satellite observations of the gamma-ray sky, looking for signatures of dark matter annihilation, have produced nothing but upper limits. Dark matter is the dominant form of matter in the universe, making up approximately 27% of its total energy budget. And we do not know what it is. Dark energy is even more mysterious. It makes up approximately 68% of the total energy budget of the universe, the dominant component by far, and we have essentially no idea what it is. The cosmological constant interpretation, in which dark energy is simply the energy of empty space, has a profound problem. When physicists calculate from first principles what the energy density of empty space should be, based on the known properties of quantum fields permeating all of space, they get an answer that disagrees with the observed value of dark energy by somewhere between 60 and 120 orders of magnitude, depending on how the calculation is performed. This is the largest discrepancy between a theoretical prediction and an observation in the entire history of science. It is not a small correction or a minor refinement. It is a fundamental failure of our best theory of matter and energy, quantum field theory, to predict one of the most basic properties of the universe. Something is deeply wrong with our understanding of the quantum vacuum, or deeply wrong with how we connect that understanding to cosmological observations, or both. We do not know which, so the two pillars supporting the standard cosmological model are both made of material we cannot identify. The model works. Its predictions match observations across an extraordinary range. But it works by invoking entities whose nature is unknown, whose properties have been inferred but not directly measured, and whose theoretical basis is either absent or catastrophically incorrect. This is an unusual situation in the history of physics, which has generally been characterized by a close correspondence between predictive success and theoretical understanding. The standard model of particle physics, which describes the electromagnetic, weak, and strong nuclear forces and all known elementary particles, is both enormously successful at predicting experimental results and deeply grounded in well-understood theoretical principles. The standard cosmological model achieves its predictive success by fitting parameters to observations using a mathematical framework that works without our understanding why it works, resting on physical concepts whose fundamental nature eludes us completely. The Hercules Corona Borealis Great Wall sits within this larger context of incomplete understanding, and its significance is amplified by that context. It is not an isolated anomaly in an otherwise complete and well-understood framework. It is an anomaly in a framework that is already built partly on mystery, that already contains within it the unresolved tensions of dark matter and dark energy, and the Hubble tension and the fundamental disconnect between quantum field theory and cosmological observations. It is one more indication, perhaps the largest and most dramatic, that our map of the cosmos is missing something, or several somethings, of fundamental importance. What might those somethings be? We have discussed several possibilities already. Modified initial conditions from non-standard inflation, modified dynamics from alternative dark matter or dark energy properties, a violation of the cosmological principle and the need for an inhomogeneous cosmological framework. Each of these represents a direction of potential revision to the standard model. But there is a possibility that we have not yet fully considered, one that is harder to articulate, precisely because it involves not just modifying the model, but questioning the conceptual vocabulary in which the model is expressed. Physics has undergone two great conceptual revolutions in the modern era. The first was relativity, which replaced the Newtonian concepts of absolute space and time with a unified four-dimensional space-time whose geometry is shaped by matter and energy. The second was quantum mechanics, which replaced the deterministic, continuous, locally real picture of classical physics with a probabilistic, discrete, non-locally entangled description of matter and energy at small scales. Both revolutions required not just new equations but new concepts, new ways of thinking about what space and time and matter and causality actually are. The equations of Newtonian mechanics were not wrong in the sense of giving incorrect predictions within their domain of validity. They were wrong in the sense of being based on conceptual foundations, absolute space, absolute time, determinism, that were revealed to be incorrect descriptions of reality at a deeper level. It is at least possible, and some physicists consider it likely, that a third conceptual revolution of comparable depth is required to fully understand the cosmos. The reconciliation of general relativity with quantum mechanics, the two great frameworks of modern physics, remains unaccomplished despite a century of effort by some of the most brilliant minds in the history of the discipline. String theory, loop quantum gravity and other approaches to quantum gravity have produced mathematical insights of great beauty and depth, but none has yet produced testable predictions that go beyond what existing theories already provide, and none has achieved anything approaching consensus acceptance. The frontier, where gravity and quantum mechanics meet, the regime of extremely small scales or extremely high energies where both frameworks must simultaneously apply, is a place where our current conceptual vocabulary breaks down entirely, where the familiar notions of space-time and causality and locality that underlie our cosmological models may not be the right concepts at all. If the resolution of the large-scale structure anomalies represented by the Hercules Corona Borealis Great Wall ultimately requires physics from this frontier, if it ultimately requires concepts that do not yet exist because the theoretical framework that will provide them has not yet been developed, then we are in a situation similar to the situation of a physicist in the late 19th century trying to explain the anomalous precession of Mercury's orbit using Newtonian mechanics. The answer exists, but it requires a conceptual revolution, in that case general relativity, that the existing framework cannot provide, and whose shape cannot be clearly anticipated from within the existing framework. The anomaly points towards something real, but what it points toward may be more radical than any of the specific modifications we have been able to articulate within our current conceptual vocabulary. This is not a counsel of resignation. The late 19th century physicist who noticed the anomaly in Mercury's precession and took it seriously, who documented it carefully and refused to explain it away, who kept the question alive in the scientific literature, was doing essential work even though he could not provide the answer. The person who notices that the data does not fit the model, who maintains the integrity of that observation against the pressure to make it fit, who communicates it clearly to the scientific community, performs an irreplaceable function in the advance of knowledge. The answer may require a Newton or an Einstein, but it begins with someone who looked carefully enough to see that something was wrong. Istvan Horvath and his colleagues looked carefully enough. Whatever the ultimate verdict on the Hercules Corona Borealis Great Wall, they have placed a question in the scientific literature that will not go away until it is properly answered. The data is there. The analysis is there. The anomaly is documented, discussed, contested, and surviving scrutiny with sufficient robustness that it cannot be ignored. The machine of science is engaged, and somewhere in that engagement, in the back and forth of observation and analysis and theoretical development, the answer is being approached, one careful step at a time. And so we come to the end of what we can say with confidence about the largest known structure in the observable universe, and the beginning of what we can only contemplate with appropriate wonder and uncertainty. The Hercules Corona Borealis Great Wall is 10 billion light-years across. It sits in the ancient cosmos, in the universe as it was between 7 and 9 billion years ago, a fossil of conditions that may have no explanation within our current framework. It challenges the cosmological principle, the foundation of our mathematical description of the cosmos. It exceeds the theoretical maximum structure size by a factor of 8. It was found in the distribution of the most violent explosions known to science, detected by satellites the size of school buses operated by human beings on a small planet around an ordinary star, analyzed using mathematics developed over centuries of collective intellectual effort, and it should not exist. We do not know what it means. We do not know whether it will ultimately require a minor adjustment to our models or a fundamental reconception of our understanding of the cosmos. We do not know whether future observations will confirm its full extent or reveal it to be smaller than it appears or different in nature from what current data suggests. We do not know whether the framework we use to study it will survive contact with the data that the next generation of instruments will provide, or whether those data will reveal it as the first clear signal of something new, something our current vocabulary cannot yet name. What we know is this: the universe is at least as large and as complex and as surprising as everything we have described here tonight. It contains structures that our best models cannot account for. It operates according to principles that we have only partially deciphered. It has been generating mysteries faster than we have been solving them for as long as we have been seriously looking, and there is no sign that this pattern will change. The cosmos is not running out of things to reveal. It is not converging toward a state where everything is understood and nothing remains to be discovered. It is, as best we can tell, inexhaustibly strange, inexhaustibly deep, inexhaustibly worthy of the attention of every curious mind that has ever turned its instruments toward the sky and asked, "What is out there?" You are living in the epoch of maximum cosmological knowledge, in the window of time when the universe is most legible, when its structures are most visible, and its history most recoverable. You are alive at the moment when the largest structure ever discovered sits in the data, unexplained, challenging everything we thought we knew, waiting for the framework that will make sense of it. You are part of the only process by which the universe has ever become aware of its own structure, the fragile, remarkable, improbable process of conscious inquiry that turns ancient light into knowledge. That is not a small thing to be. That is not a small moment to inhabit. The Great Wall is out there, 10 billion light-years of matter and mystery and unresolved implication, and you know it exists. And you carry that knowledge in the same universe that contains the thing itself, and in some way that is very difficult to articulate but very difficult to dismiss. That matters. The night sky above you tonight contains the light of galaxies whose positions, if you could map them at sufficient depth and scale, would trace the outlines of structures we are only beginning to understand. The darkness between those points of light is not empty. It is full of dark matter and dark energy and gravitational influence and the faint remnant warmth of the Big Bang and the stretched light of explosions that happened before the Earth existed. And somewhere out there, in the direction of a kneeling hero and a northern crown, embedded in the ancient universe at a distance that light has spent most of the age of the cosmos crossing, is something enormous and unexplained and real. It was there before we found it. It will be there long after every instrument we built to find it has fallen silent. But for now, in this brief and remarkable window of cosmic time, we know it is there. We looked, we measured, we found something that should not exist, and we have not looked away.